Hi there students, this is Dr. John, your physics and math professor, and today we have another force problem. This is where we have a test car that's crashing into this immovable stone wall, and the car initially is moving at 24 meters per second, and then when it bounces off the wall, it goes backwards at 8 meters per second. Now initially the car has this green crumple zone. You'll notice most cars have this bumper at the front or at the back, so if you get hit, that crumple zone crushes up and absorbs the impact so the people inside the car don't have as big an impact. And what it actually does is it extends the time of the impact. So initially, this change of momentum, this impact time is 0.9 seconds. And we're supposed to find the force at which the wall pushes back on the car during that time. The force that the wall exerts on the car, which of course, from Newton's laws, we're going to check that in a second, is the same as the force that the car exerts on the wall. And then afterwards, we're going to check the same calculation if there was no crumple zone. You just had basically a steel structure, a really strong structure, and the time of impact was now 0.080, which is like 1/10 of that, a very quick impact time. What would be the force that the wall would exert on the car, and also sequentially, the force that the people inside the car would feel as well, and that they would exert on the windshield or on the steering wheel. But first of all, I'm just going to quickly review Newton's laws for you. So here we have Newton's 3 laws of motion. One is that if something is moving, it's either at rest or it's got a steady inertia, a steady movement. Like here's this block on ice, the ice that has no friction, and it's just sliding along. It's going to continue to slide if there's no unbalanced forces. That is, what Newton is talking about here is the sum of all forces, or sometimes you'll call it the net force, the total forces. So if there's a force in this direction, and there's no force in the other direction, that's a net force. So if there's no net force on this object, it's going to continue to move as it's moving. That's sort of common sense, but Newton put it into an equation, so that helped us. And then the second law is, what if there are unbalanced forces? What if there's more force going this way than going the other way? Well, then this block of mass m is going to experience an acceleration. How big an acceleration? Well, it depends on how big the force is and how big the mass is. But the bigger the mass, the smaller the acceleration. If you just have two of these, let's say you have the acceleration and you have the force, you can find the mass, because the mass is going to be equal to the force over the acceleration. You can just solve that, and you can solve for one or the other. So this is a really cool equation. Then Newton has this third law of motion, which is that for every force, there's an equal and opposite force. And I know for some people that sounds really confusing, but let's pretend here that there's another box right here, and it's pushing against this box. This box is actually the one that's pushing. You're pushing this box, which is pushing this box. Now notice this box here would exert a force on the blue box, which is in the direction of that arrow, and the blue box would also exert a force on the green box in that direction. However, these forces don't cancel each other out. It's just that forces always come in pairs. And so this one here would push this box this way, the blue one would push that box that way. They would both tend to push each other apart, to separate from each other, and so they actually have the same effect. It's just that we count them in pairs, and that really helps us to understand why things move. So those are Newton's 3 laws, and that's why I said here, if this car hits the stone wall and it exerts a force on the stone wall in this direction, the stone wall is going to exert a force in the car on that direction. And of course, if the car is exerting a force in that direction, and the stone wall is exerting a force in this direction, notice this will push the car away, this will push the stone wall away, but it can't. So the car has to move away this way because the stone wall is immovable. Quick review of Newton's 3 laws. Now let's get to this specific problem. When we do a problem like this, we always start by collecting the different things that are given. We already have the mass written down here, so I'm just going to leave that there. And then we have the initial velocity, which is going in this direction. We're going to count this as positive. Count that direction as positive, so that's going to be positive 24 meters per second. And then we have the final velocity, which is what? It's negative 8 meters per second. Because we always want to create a direction that's positive. Usually you go to the right and up is positive, but whatever is convenient for you for your problem. So these are the 3 things that we have here. And then of course we have these 2 times. So we're going to start off by calculating it with time number 1. What do we need to do to calculate the force? Well, remember we had from Newton's law here, we had that force is equal to mass times acceleration. This is either way, the force that the car exerts on the wall or the force that the wall exerts on the car. Forces always come in pairs. That's what he said with that third law there. So what is the force that we have? Well, we have the mass of the car. That's the important piece of information. Secondly, but we don't have the acceleration, because that's the other thing that we need. How do we find acceleration? If you remember from your very basic, the acceleration equals the change in velocity divided by the change in time. We like to use Greek letters. This is the capital Greek letter D, and so we feel really smart if we use Greek letters. Later on, when you're doing calculus, you're going to change this into using the English letter D, and you're going to go the derivative of the velocity with regard to time. That's the same as this, only the derivative is an exact point at a specific point. This is more spread out. We're using a spread out time period of 0.9 seconds, an average sort of acceleration here. So this is where we use delta. So we want the change in the velocity over the change in time gives us the acceleration over that period. So let's just start off by figuring out what the change in velocity is. Well, notice here, normally we would say the change in velocity would be equal to the final velocity minus the initial velocity, or velocity zero. Final velocity is going this direction. Let's just put the actual numbers in there, 8, and then we're going to subtract the initial velocity, which is 24. So the change in velocity is minus 32 meters per second. Remember, we said that this was the positive direction, so it has a change of velocity of 32 meters per second in that direction, which is sort of what we would expect. We can actually do this without all of our clever thinking here. Just realize it's initially going this way, 24. It's later on going this way, 20 by 8. So the change here is going to be this plus this. You're going to make a double negative here. If you want to count this as positive and do this minus this, you can do that way as well. But I did this more the way that you would sort of tend to think of it, final velocity minus initial velocity. So the change in velocity, I'm going to write that up here. I'm going to go the change in velocity is equal to minus 32 meters per second. Now we have the change in velocity. We can use this equation here to calculate the acceleration. So we're going to do this in two specific cases, because we have this case and we have this case. So maybe I'll use different colors for that, and I'll erase a couple of things just to give myself some more space. Okay, I jumped ahead here a little bit for you. I rewrote this here, that the acceleration is equal to delta V, or the change in velocity, over the change in time, over the time period that velocity changed. So I rewrote these over here. We said 32. I'm not too worried about the negative signs, because we know later on we're going to want the force in that direction. It's just going to be a numeric force. We're not going to use a negative one, because we're going to say the force that the wall has on the car is going to be positive. So here we have the acceleration equaling 32, which we got from here, divided by the change in time. And then over here, this with no crumple zone, we have the same change in velocity, 32 over 0.08. I just did the calculation for you just to save some time. So this one is 35.6. What is that? What's the units? Meters per second squared. Notice this is meters per second, and here's seconds. So this seconds goes in the denominator. Or you take this one here, flip and multiply. So it's m over s times 1 over s. So it's like this, divided by this. This is the longer division sign. So if we want to say this here, we're going to flip this and multiply. Taking this, flipping and multiplying, that's meters per second squared. However you want to envision it. So that's the units for acceleration. I'll write the same ones over here, meters per second squared. Notice this here is about 1/10 of this. So you'd expect this to be about 10 times higher. This is 35, that's 400. It's reasonable. We can also do this roughly in our heads. If we notice this here is about 32 divided by about 1, so it's going to be about 32, and it is just a little bit more. We can also do this one in our head. It's going to be about 320. It's a little more, it's 400. So those things all seem very reasonable. Now let's take the next step. We've got the acceleration of the car as it hits there. It's actually being accelerated though in that direction, because it's being slowed down. So it's being accelerated in that direction. So we could put a negative there if we wanted to, like we talked about before. Not necessary though, or sorry, over here. Over there, there we go. Now we want the force. I'm going to do these in different colors. The force that the wall pushes on the car when it has the crumple zone is going to be equal to the mass times the acceleration. So it's going to be 1350 times 35.6. And over here, it's going to be the same, 1350 times 400. Quick calculation, let's get what those numbers are. Okay, here I did my calculation. This one here, 48,000, and this one, 540,000. We probably don't want to put it like this, and we also want to think about the significant figures. Notice here we have 1, here we have 2, here we have 2 significant figures, and here we have 1 significant figure. So, I don't know, let's just keep it to maybe 2 significant figures, and we're going to go 4.8 times what? Remember, with the decimal previously is over here. We move over 1, 2, 3, 4. So this is going to be 10 to the 4. And that's newtons, of course, just like this is newtons. And this one over here, the same. If we're going to want to write this in scientific notation, 5.4 times 10 to the what? We start off with a decimal here, we move over 1, 2, 3, 4, 5. So this is 4.8 times 10 to the 4 newtons. This is 5.4 times 10 to the 5 newtons, again, about 10 times higher. So just here's something interesting for you to notice. By the way, like and subscribe, and we'll see you in the next video. But one more thing to notice. Notice these two things are the acceleration here. This is the acceleration the car will feel in that direction, that the wall, because of the force the wall pushes on it. This is the acceleration. Now remember, the acceleration of gravity is 9.8 or about 10. So this is about 3 Gs. So this is about 3 or 4 Gs, or 3 times the acceleration of gravity, which is fairly reasonably high. It's maybe what you might feel in an airplane that, an Army airplane that goes fairly fast, but not one of the supersonic airplanes like in Top Gun. Those would be much higher. This one notice over here, this one would have 40 Gs. In a Top Gun airplane that does extremely sharp turns, you might experience 10 Gs, and at 10 Gs you would tend to black out. So this is 4 times as high as extremely highly trained test pilots who might black out, 4 times as much as that. So that's why we don't have cars without crumple zones, because the amount of force that you would feel and the acceleration that passengers feel is so high if you have to come to a sudden stop that it would basically kill them pretty well every time. So we want to have this crumple zone. Greatly reduces the amount of G-force that you feel as a passenger inside the car, and also it would reduce the destruction on the engine and other parts of the car and stuff like that. So I hope this helped. Again, like and subscribe, and I will see you in the next video. Bye-bye.